Hello and welcome to Toddcast number 9. Um, as has been the case with all the previous Toddcasts, this is sort of a foundational or review video. And the first probably 20 Toddcasts are all going to fall in that sort of category, knowing the rules. But these are ones, this one especially today, we're going to draw the bond line representation of atoms, the standard way we usually represent molecules. Absolutely critical that you are incredibly anal, pay incredible attention to detail in writing these structures because it helps us to fully grasp how the molecule exists in three-dimensional space. And also, when it comes to grading on the exams, you're going to be um, knowing the reaction is important, knowing the chemical is important, knowing the molecule is important, but also knowing the structure. And so if you draw them incorrectly, you will end up losing points for the incorrect drawing and run the risk of possibly not showing the actual reaction as it should be shown. So, not to start with the overbearing attitude about it, but absolutely critical that we pay attention to it. So, we alluded to it a little bit in the one of the previous podcasts. So, just make sure this makes sense. But we took a structure. And I'm going to draw the formula in just to be kind of complete on this one. But if you count it, there's 6 carbons and 14 hydrogens. In bond line representation, you only identify key elements, key heteroatoms. So not carbon, not hydrogen, but oxygen, nitrogen, sulfur, phosphorus, other compounds. Carbon doesn't get designated with a C, but it's an intersection point of 2 lines. So you'll see where 2 things come together, we'll designate it. And then H's we ignore except if they are on one of those other atoms. If there's a pH2 group, an SH, an OH, an NH2, we'll represent the H's on those groups. But H's on carbon get omitted, and carbons are just intersections of lines. So to do this very systematic approach, we're going to take this structure, we're going to shed the H's, get rid of all 14 H's, and represent just the 6 carbons initially. So this is just that component right there, just the 6 carbons. Okay. Then we're going to identify their hybridization by drawing the structure with accurate bond angles. So in this case, everything is sp3 hybridized. All carbons have 4 other atoms attached. So their steric number is 4. So everything's sp3. So I'll make note of that. So sp3 needs to have a 109.5-degree angle. So we redraw this skeletal structure here as such. So it's still 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. So I have my 6 carbons, but now with accurate angles. So that's 109.5, 109.5, 109.5, 109.5. Then lastly, we get rid of the carbons and just make an intersection of 2 points. So ultimately, we're going to represent C6H14, and let's just say it's hexane. So N-hexane or linear hexane. We're going to ultimately represent it by 1, 2, 3, 4, 5, 6 points, 6 vertices. 2, 3, 4, 5, 6. So C6. And then we have to know something about how many H's. And so we're going to cover a topic called unit unsaturation as we start moving along a little bit further. But mention unsaturation and saturation, saturated with H or unsaturated with H when we're referring to melting points. We want to just emphasize for this structure here, 6 carbons, there's always 2 at the end and all the rest in the middle. The middle ones can only have 2 H's each. The end ones can have 2 plus the one dangling off the end. So for every carbon, there's 2, 2, 2, 2, 2, and then plus the 2 dangling at the end. So for 6 carbons, 6 times 2 would be 12 plus 13, 14. So 14 H's means it is fully saturated. Okay, so first structure down. Okay, this one kind of the same thing. The only difference here is it is 1, 2, 3, 4, 5 carbons with 1 carbon coming off. We refer to these as isomers. Isomers have the exact same formula. So again, it's C6H14. Let's just double check. 1, 2, 3, 4, 5, 6 carbons. H's are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So C6H14, but we're going to draw the skeleton a little bit different. So again, we want to start by just getting rid of the H's. So if we do that, you have 5 carbons in a row with a carbon coming off the second carbon. And I'm calling this the second carbon because in theory, we could count from right to left or left to right. And so the rule is always assign the lowest possible number, the lowest possible address to whatever is dangling off the side. So if this is a 5 carbon chain, 1, 2, 3, 4, 5, and has something coming off of that carbon, rather than calling it the fourth, I'm going to call it the second because 2 is a lower number than 4. So it's known as 2-methylpentane. But we're not doing this for nomenclature. We're doing this for showing the bond angles. So the skeleton, the backbone, is going to be just like this up here, but only 5 carbons and then an extra carbon coming off. So we will represent it as up, down, 5 carbons, and then this one group sticking up. Bond angles again are 109.5, 109.5. This one ends up, it's going to be probably a little bit bigger than 109.5 visually, but it's supposed to be represented by 109.5 as well. Okay, and once again, we get rid of the carbons and just make intersections of lines, their vertices. So this structure will be given this shorthand. You absolutely positively have to have the right zigzag. If you don't zigzag it right way, that actually will cause visual issues in seeing how the molecules react. So make sure you get used to the zigzag. Spending a lot of time doing a simple translation, but you're going to do this so much, you want to get it really down pat the first time, do it really well this time so that you get in good habits. So like learning anything new, you have to go through it methodically in slow motion until you get it down and then do it faster and faster until it's a reflex. Last but not least, I'm going to do an alcohol, 1, 2, 3, 4 carbons. So bute, OH, so butanol. The OH is on carbon 1, so we're going to do 1 butanol. So 1 butanol will have the formula C4H10O. But we can also represent it as C4H9OH. And we just tend to have rules we make up as we go along. But when it's specifically an alcohol, adding the OH designates that H as being different than all the rest that are on carbon. And so I like this formula. It's how we're going to draw it most of the time, although technically that's also the same formula. Okay, again, skeleton, get rid of the H's, except when the H is on an atom other than carbon, we leave it. We emphasize it. That's why this formula might be a little more helpful. So we bring it over, 4 carbons and an OH. We draw the up, down, up, and then the O is going to be like the carbon, going to come down. So again, 109.5, 109.5, 109.5, and 109.5. Get rid of the carbons, and you represent it as such. So you will have to understand what these structures are. So we're going through a methodic way of going from this drawn out structure to this. But reality is most of what we're doing in chemistry is you're going to be shown molecules in this fashion. You're just going to have to automatically know that it's a carbon with H's on it, carbon with H's on it, carbon with H's except for the OH at the end. And so you're going to have to fill it in mentally as needed. But we're going to do most of our representation of molecules in this bond line formation. Okay, so let's do it from a more, I don't know, instead of a mechanical computer generated image, there's a hand-drawn image. So I have carbon, 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 4 carbons. I have a bromine on the second carbon and an OH on the third carbon. OH, it's more higher priority functional group. So this is 2-butanol, and it's a 3-bromo-2-butanol because carbon 1, 2, 3, 4 would put the lowest number on the OH, 2 rather than the 3. To draw it out, again, I want to go up, down, zigzag. So there's my zigzag. I want to emphasize that you always extend up or down from points. So I want to draw this up and this OH down and ignore my other H's. And then that, those same bonds. So you ultimately put the BR here like it's shown, the OH here like it's shown. Be very careful not to do this. Do not draw it in the 1095 angle. Draw it so that everything has space. Everything is spread out. So it's supposed to be an accurate three-dimensional representation. So consequently, this would not be accurate. Okay. Let me get rid of my drawings. Toss out another one. So this, everything's linear SP, or I mean, lines are SP3, so their bond angle is 109.5. But if you recall, triple bonds are SP, double bonds are SP2. So I want to emphasize that because that's going to affect how we draw it. So the bond angle around an SP carbon is 180. It's a linear structure. And SP2 is trigonal planar with bond angle 120. And so when we draw our bond lines, structures, bond line representation of our molecules, we have to keep that in mind. So the zigzag is for SP3. When we get to this, we have to be careful what we emphasize. So I'm going to draw this carbon down, up, down. So if I went like this, that is incorrect because this angle is not 180. So this actually has to be like this. And then you can come off to an SP2, which has to be like this, which then will be something like that. So let me put the prettier drawing up. That's what we're going to set it up. So after we did the carbon, notice same story, went up, down, had to go straight down for this one. Double bond went up and double bond went down. Just if you draw it like this, again, this will be points off. If you draw a double bond like that, yeah, it's still close enough. We'll probably get away with that. Triple bonds have to be linear. Okay, so we're drawing our structures. So now for the more practical aspect of things, you're going to have to convert and visualize the way things are set up. So for ferulic acid, if I drew it like this, it'd be very much a pain. So again, get rid of all the hydrogens and make carbons just points. I'm only going to have 1, 2, 3, 4. So I'm going to help myself this time. I'm going to have an OH, I'm going to have an O, an O, and an OH to worry about. Everything else, those letters are going to go away. I'm going to start with the middle ring. This middle ring here, carbon, 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 carbon. Here, double bond here, double bond here, double bond here. I'm going to ignore my H's, and I'm going to ignore the other systems. Second thing I'm going to do then is add in the non-H's. So I have my O coming off here, my O coming off here. There's an H here, so I'm going to ignore it. H here, ignore it. H coming off here, ignore it. And then a carbon coming down here. So I'm going to draw the O, and the bond to carbon. Then next on the agenda, going to put in those groups that we just highlighted. So the groups as we see them are O with a CH3. So we can represent it that way, or I can do it O with a line. So if I wanted to, I could also, instead of doing CH3, it's also valid to do that. The OH is its own separate entity. And then this group is known as carboxylic acid. So CO2H represents that functionality. You can also represent it in its structural nature. So if you wanted to, you can also represent it like that. So that's just as fair. So couple different options, but the key thing is get the backbone, get the foundation down. Okay, so want to translate in verse direction. So we did this molecule in a previous podcast, talked about how these are all sp2, sp2, and sp3, and then the various groups on there. So I'm going to start with the skeleton. So if I'm translating the other way around, this ring right here, carbon, 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 carbon. Middle ring is a carbon, 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 oxygen. And over here, I have the same thing, carbon, 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 carbon. So I've taken care of that ring, and that ring, but nothing on there. I've taken care of my 5 OHs. Okay, so the OHs will be here, here. This one will be here. This one will be here, and this one will be here. So I can put in my non-H's, my OHs that I just identified. And then last but not least, I got to put in my H's. And so this is in your mind, you must translate how many H's you have at each spot. So this carbon can make 4 bonds, it has a bond to carbon O, C, and C. So it doesn't need an H. This carbon, 2 bonds of carbon there, 1 bond, so it only has 3 bonds, so an H. 2 bonds, 1 bond, so an H. This one, 1, 2, 3, 4 bonds. It's good. 1, 2, 3. So this needs an H. So I need an H here, here, and here. This carbon has an O, a C, and a C. It also needs an H. This carbon has a C, C, and an O. Also needs an H. This carbon here has just 2 bonds of carbon, so it needs 2 H's. This carbon 4 bonds, this carbon 4 bonds, this carbon 4 bonds, this carbon 3 bonds, it needs an H. This one needs an H. So I need an H here, 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 and then 2 H's there. So add in the H's. Those are the ones I needed on this structure, here and here. And then need these here, and again, 1, 2, and then 2 on that carbon. So this representation is easier to draw than this one. Atoms get very crowded here, it gets convoluted. So this points out the reason we do it this way is because most of the chemistry we're worried about is going to be the other groups on the carbon. And so by emphasizing those and putting everything more into the background, we can see what's going on or focus on the key functional groups, the key components of molecule in the reaction. Okay, so why we do this? So this structure, pretty common, mentioned the concept of an antioxidant. So when you have well, this is going to be known as a benzene ring or an aromatic ring. When you have a 6-membered carbon ring that's set up like this with 1 OH called a phenol, when you have 2, it's a catechol. Catechols typically are next to each other. But what this does is it offers the possibility to lose the 2 H's so it gets oxidized, which will produce something else, making an antioxidant. So when those H's get lost, I now have a double bond here. Double bond is gone here. This double bond is there, and double bond there. So it's a chemical reaction where you have to recognize what has changed. And because it's drawn the way it's drawn, you can emphasize that 2 H's are lost. You can visually see it very quickly. So this is the beauty of this method. So far, so good. Okay. I know it's probably a weird thing to toss there, but as long as we're on these structures, must know steroids just for being a scientist, but want to emphasize very typical ring structure. So we bring this up because just recognizing the way things exist in 3-dimensional space will matter, and we'll go into this down the road. But steroids have this 6-member ring connected to another 6-member ring, to another 6-membered, another 5-membered ring. And then the CH3s are telltale. This can vary. This can vary from one steroid to another. But these are molecules then that are very, very massive with a lot of carbons, easier to draw this way to emphasize the structure. A solid line graphically represents this OH in front of the page. So it isn't in the plane like the straight lines represent thin lines. It represents the CH3 coming out away from your page, out away from your page, and out away from your page. If it was going back, we draw it as a dash. So this is just, I guess, drafting 101, the way you draw structures. Notice that this backbone is the same as this backbone. But what has changed? This group has changed. This CH3 has disappeared and become a pi bond in its place. And this OH has turned into a double bond O. So double bond O and OH changed, and that CH3 left. There isn't a lot of difference between the different steroid hormones. And so the fine line difference, we'll get into more detail. This is completely planar. This is not. That subtle difference allows it to bind an active site or a receptor differently than this. So these signal for two different functions because of the different functional groups and the slight structural differences in that first ring. And then progesterone, one more in that. And I'm assuming this is something you'll get in a histology class or some class where you'll study, for instance, the female hormone cycle or just the hormone messenger molecules in our body. But the reason I'm emphasizing it is just to say that these common structural backbones, when we draw it this way, you get used to just seeing how things align. And if you know something about this one, you know something about this one or this one. Okay. Eicosanoids. Fun fact, eikos is Greek for 20. So eicosanoids, very common 20 carbon species, are also messenger molecules. And the difference is the ones we did on the previous page, hormones, are made in a gland and then they're sent through the bloodstream to some target. So they send general messages through that can travel anywhere in the body, whereas eicosanoids are local messenger molecules. They're made by a cell to send a message to a neighboring cell. So, like if you think what a pheromone is the same thing, messenger molecule, but that's from one point to another point. So from one species to, or I guess one critter, one animal, one plant, whatever it is, sending it to a neighbor. Whereas eicosanoids, these get passed within the body. So one cell to another cell in the same body. And so they trigger for things like pain, swelling, muscle contraction, asthmatic response, heart fluttering, uterine contractions during pregnant or birthing. So they do a bunch of different things. And so a generic prostaglandin is 20 carbons. Let me just count to make sure. One, it's the one with most O's, so this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Perfect. You have the double bond, and this is again cis designation because the double bond can't rotate around it, so these are on the same side. This is trans. You have your carboxylic acid group that's missing its H, so it's negatively charged. And notice again, at every point, this is point down, so the OH is coming down. This is point up, so it's going up. This is point down, so OH is going down. You always draw your substituents in the direction of the point. So if you think of that like an arrow, that OH has to go down. So again, do not draw it like that. You do not draw it like that. It doesn't go on the inside. Okay, so standard conventions for drawing these. So the generic prostaglandin, I'm going to say specifically, there's different names for them, but they're historically named not based on what they do or any creative methodology. But it comes down to the first one discovered was prostaglandin A. Next one discovered, they call it B, C. Very common if you discover things in labs, if you learn something new. E2, 2 represents 2 double bonds outside of the ring. So A2, 2 double bonds outside the ring. Thromboxane, if the name triggers any knowledge, thrombin is what causes clotting. So thromboxane is the messenger molecule that we release. So upon cell death, the cells get exposed to the outside air. It causes arachidonate, the precursor molecule, to be oxidized in a very specific way. We modify it, our cell modifies it to send the message. So for instance, if you're bleeding, this messenger molecule, you want to send that immediately to a neighboring molecule so you know to form thrombin and start sealing off. If it was a hormone response, one, it would take a long time, and number two, you don't want to clot everywhere in the body. You only want to do it locally where you need it. So local messenger molecules. I've chosen these not because they're important to OCHEM, but wanted to pick structures that are very complex to emphasize the zigzag, the double bonds, trans and cis, the ring system, and then everything coming point up, point right, point left, whatever way it's pointing. We always draw those functional groups on them as such. Okay, so just to emphasize carbon 1, carbon 20, and I guess it's not a bad idea to know that you end up getting double bonds will always form between carbons 5 and 6. The ring is involving carbons 8 and 12. And 9 and 11 will have things coming off of them. And then 15 will have something coming off of it. So if I match one structure to the next, you'll notice they all have the same thing. But this hopefully is one that just a few examples, you'll get good at it. It's just something that it's a pain at first, but once you get used to it, it becomes easy. Just be really, really anal your first time you do it. Anyway, thanks for being a part of it. And I am going to go ahead and end this podcast and see you in the next one. Thanks for joining. Bye.